Hello everyone. Now next we will see example 2.15. So consider the same Euler equation ux plus uy equal to 0 with the initial data u at x0 equal to 0 for x less than or equal to 0, x by alpha for 0 less than x less than alpha, and 1 for x greater than or equal to alpha. So here you can see that the initial data is increasing. Okay, so the derivative will not be less than 0. So there will not be any critical time. Now the critical time yc is minus 1 by h dash of s. As I already told that for yc to exist, this h dash of s must be negative. So h should be decreasing. Now what is h here? H is this function. Now what is h dash? We denote this initial condition by h of x. H of x is this function 0 for x less than or equal to 0, x by alpha for 0 less than x less than alpha, 1 for x greater than or equal to alpha. Now what is h dash of x? H dash of x is 1 by alpha, and this is always positive. So h dash of s cannot be since it is always positive, there is no critical point. The reason is that the initial data is increasing here. So we expect that there is no critical time where the characteristic intersect. Now we will see what is the classical solution. So the classical solution, as we did in the last problem, same. Characteristic equation xt equal to u, yt equal to 1, ut equal to 0. Initial condition x at 0s equal to s, y at 0s equal to 0, u at 0s equal to h of s. Then this also we have did in the last problem, same thing, x is equal to s plus h of st, y equal to t, u equal to h of s. So s equal to x minus uy, so u equal to h of x minus uy is the implicit solution. Now here h is different. Up to this all steps are same. We got the implicit solution. Now we will try to write u explicitly. For this we have to see the projections. We have x equal to s plus, from here we have x is equal to s plus h of s y. This t is y. Now what is h of s? We already have what is h of s here. This is the initial, this is h of s. So we have to substitute h of s and we have to multiply with y and add s. So we have first term will be s for s less than or equal to 0. Second one will be s plus s by alpha y for 0 less than s less than alpha. And third one is s plus y for s greater than or equal to alpha. So from here, so I got x. Now next step is to write s. From here I have to write s. So the first term is s is x itself for x less than or equal to 0. From here I have to find s. So second term is x equal to s into 1 plus y by alpha. So from here s is equal to, here one equality is there, s is equal to x alpha by alpha plus y. Here I have taken LCM. Okay, so it is alpha plus y by alpha. So x alpha by alpha plus y. So this is s. So I have substituted here x alpha by alpha plus y for 0 less than x alpha by alpha plus y less than alpha. And third one is x is equal to s plus y, which implies s is equal to x minus y for x minus y greater than or equal to alpha. So we got s. I can write s in this way. S is equal to x for x less than or equal to 0, x alpha by alpha plus y for 0 less than x less than alpha plus y, and x minus y for x greater than or equal to y plus alpha. Now I can write u from here. How u operates. U is a function of h of s. We know how h is defined. H takes the value 0 if x is s is less than or equal to 0. So you can see here x is less than or equal to 0. So h of s will be 0 for x less than or equal to 0. Now second term is x by alpha. So by alpha, when I do, alpha will get cancelled. So it is x by alpha plus y for 0 less than x less than alpha plus y. And third one is 0. Third one is 1 for x greater than or equal to alpha. So it is 1 for x greater than or equal to y plus alpha. So we got u explicitly. So we expect that this is our classical solution. So we have the classical solution is this: u of xy is 0 for x less than or equal to 0, x by alpha plus y for 0 less than x less than alpha plus y, and 1 for x greater than or equal to y plus alpha. Now we will see the case when alpha tends to 0. So here, when alpha tends to 0, what will be u? U will be 0 for x less than or equal to 0. Here it will be x by y for 0 less than x less than y, and 1 for x greater than or equal to y. So this is the solution when alpha tends to 0. But what about the initial condition? You can see that the initial condition is, this is the initial condition. When I put alpha tends to 0, here I have when alpha 0 less than x less than 0. So this term will not be there. So it will be 0 for x less than or equal to 0 and 1 for x greater than or equal to 0. So when alpha tends to 0, I have 0 and 1 values. And this is not same as the solution nature. In solution, as alpha tends to 0, I have 0 and x by y in a region and 1. So you can see that when you make a change in the initial data, the solution is not changing in the same way. Okay, so there is a problem here. Actually, this question is an example of expansion wave, because here waves are expanding. So from the initial data, we got a different solution in u of x, where the nature of the solution was different. Okay, it is not same as the initial data as alpha tends to 0. But this is not the case if we consider the previous example. That is in 2.14, where we had a shock. We see that as alpha tends to 0, both are same. Both the initial condition and the solution. Initial data are same as the shock weak solution, because here we have 1 and 0. And the initial data also, there we had 1 minus x by alpha. So when alpha tends to 0, we will get 1. So we have only two values, 1 and 0. So in what we conclude is that in example 2.14, as alpha tends to 0, initial data and the shock weak solution both are same. But in example 2.15, as alpha tends to 0, initial data is not same as the solution. There we got the classical solution. They are not same. Actually, in example 2.14, waves are compressed. It is an example of a compression wave. So these are the difference between them. So here also we can see that the weak solutions are also not unique. We can also denote the solution, but in the case of example 2.15, we see that this is not unique. Now we will see the next topic, that is the conservation law. So we see that so in the first case we have seen the Euler equation, where the equation was uy plus dou by dou x of, here we had half u square. That was the Euler's equation. So in general we will consider it as f of u. So in Euler's equation, f of u was half u square. So when you took derivative, we got ux. Okay. So this is the general case. Now we will see the general case. So equations of this form are called conservation laws. If an equation can be written in this form. Here y usually represent time. Okay. So a time derivative will be there, and if we are able to write it as dou by dou x of some function in u, then such equations are called conservation laws. Now we consider the initial condition u at x 0, which is u minus for x less than 0 and u plus for x greater than 0. Now we write the weak formulation. As usual, we will assume that the solution takes the form of a shock wave, and in the solution we have u is u minus when x less than gamma of y and u plus when x greater than gamma of y. That is, the discontinuities lie on gamma of y and there is no problem in the left or right of gamma of y. So our aim is to find the curve gamma of y. Then we have the solution, because u minus u plus we already have from the initial condition. U minus u plus we have. So we are assuming that the solution will have a shock wave and it will be of this form. U of xy will be u minus for x less than gamma of y and u plus for x greater than gamma of y. So our only aim is to find gamma of y. What will be the curve gamma of y? So for this we integrate the PDE equation 1 with respect to x in the interval x1 x2, where x1 is less than gamma and x2 is greater than gamma. That is, gamma lies in between this interval. So as we did in the first case, in the weak formulation of the Euler equation, in the same way we are doing. Okay, there we integrated from a to b, but here we are integrating from x1 to x2, because this need not be always bounded. So we are taking an interval x1 to x2. So as we did in the last case, in the same way we are integrating from x1 to x2. Here when we integrate with respect to x, dou by dou x will not be there. So f of u, now u is a function of x and y. Here we are considering the dummy variable theta. Theta comma y limits x1 to x2 equal to 0. Now as we did in the Euler weak formulation of the Euler equation, the same steps you have to do. Only difference is that here the limit are from x1 to x2, and f, the general term f is written, f of u is written. There you had half u square. Instead of that, here you have f of u. So again we are integrating this from x1 to gamma of y plus gamma of y to x2. And here we have applied the upper limit minus lower limit. So we mark it as equation number 2. We will take this term, simplify it and substitute it here, as we did in the weak formulation of Euler equation. So the same step you have to follow, so I am not writing it again. So there in the weak formulation of Euler equation, we got this as dou by dou y of this quantity. Here we have to apply the Leibniz's rule. So this is the derivative of integral, so it becomes integral of derivative. Then you have to apply the upper limit minus lower limit. So this will be a constant term. So here gamma of y, that we are denoting by u plus and u minus. So we will get these two terms. These are the same step. Okay. Then for the first two steps we have dou u by dou y is minus dou by dou x of f of u. That we are substituting here, minus dou by dou x of f of u. So dou by dou x of f of u. And here integral sign is there, dou by dou x of f of u. So the integral and derivative terms get cancelled. So you have f of u minus f of u limits x1 to gamma of y plus f of u limits gamma of y to x2. Same steps as we did in the Euler's equation weak formulation. Put upper and lower limit, simplify it. So we have arranged the terms like this: f of u plus minus f of u minus plus f of u at x1 y minus f of u at x2 y plus u minus minus u plus into gamma y. Now substitute this thing in equation number 2. So when you substitute in equation 2, we see that these two terms will get cancelled. So we have f of u plus minus f of u minus plus u minus minus u plus gamma of y equal to 0. Here we take these terms to RHS, do simplification here. So we will get gamma y equal to, gamma y is nothing, This is gamma. Actually, here I have, this is actually derivative. Okay, dou gamma by dou y. It represents derivative of gamma with respect to y. So it is equal to f of u plus minus f of u minus by u plus minus u minus. This we denote the numerator by this notation, box f, and this we are denoting it by box u. This is a notation only, and this equation 3 is called the Rankine Hugonoid condition. So if we substitute f equal to half u square, we will get the earlier condition that we have already proved. Okay, so this is the important relation. So we already know that the characteristic, when the characteristic meet, they carry the initial information of the solution. Okay, so when the characteristic emerge, suppose there is a shock is formed, and if the characteristic enter through the shock, and when it leave, if it carries the information of the shock, then there will be some creation of information, which should not happen, because here we are seeing it is against the law of thermodynamics, in which as time increases there may be decrease, but new information cannot be created. Okay, informations can be, as time increases there may be depletion may be there, but the new information or new material need not be created. So if the characteristic emerges from the shock, then it will carry new information. Okay, so it is so this should not be there, and hence we say that the entropy condition must be satisfied. And what is the entropy condition? Entropy condition says that the characteristic must enter the shock waves and are not allowed to emanate from it. So it should not propagate from it. It should enter the shock wave, but it should not carry the information that the shock wave has. So that is the entropy condition. And for satisfying the second law of thermodynamics, this entropy condition should be satisfied. So the conservation law is also written like this, that is uy plus fu ux equal to 0. Here we see that speed of the characteristic is fu. We have already seen this. When we saw the linear equation, here we had c, uy plus c ux. There we saw, there we told that c is the speed of the wave. In the same way, here speed of the characteristic is fu. And also the entropy condition imply that fu at u plus should be less than gamma y and should be less than fu at u minus. This condition, if you put fu as u square by 2, you can see that this condition imply that u plus should be less than u minus. Actually, the shock solution is valid only if u plus is less than u minus. It means that if we have a characteristic, okay, if one characteristic which is at back have a greater speed than the characteristic which is at front, then there will be a shock will be formed. That is, the two characteristics may intersect. Okay, so a characteristic which are at back, if it has a more speed than the characteristic which are in front, and these characteristics are moving, so the characteristic which are at back will overtake this, and they will intersect at a point. So at that point there will be a problem. Okay, so that is u minus is greater than u plus. That is, when u minus is greater than u plus, then only a shock solution will be valid. So we stop our theory here, shocks, wave solutions and conservations laws here. It is a little bit tough topic, but you study whatever is discussed in your notes. Okay.